So in section 13.2, we're going to be moving away from two-dimensional space, and we're going to talk about three-dimensional space. So if you notice this coordinate system that we have, it has an x-axis, it has a y-axis, and then it has our three-dimensional space. So we also have a z-axis. So when I say three-dimensional space, I just mean a coordinate system with an x, a y, and a z coordinate. So sometimes we call it R3 for real numbered space of 3 dimension. If I plot a point, say the point 3, 2, 4 in my coordinate system, it's still going to be an x, a y, and now we have our z value. You simply count. So my x coordinate is 3. I'm going to go 1, 2, 3 in the x direction, positive x direction. Y is 2, so I'm going to go 1, 2 in the positive y direction. And z is 4. So from this point here, I'm going to go up 1, 2, 3, 4. And then this is roughly where 3, 2, 4 will be. Ooh, my pen looks awful today. Now just be careful, because if we have negative values, we have to go in the opposite direction. So the next point, negative 3, 0, negative 1, we have to go negative 3 on the negative x. So 1, 2, 3 in the opposite direction. We're moving 0 in the y direction, but we're going to go down 1 in the z direction. So this would be the point negative 3, 0, 1. So we're going to build from points to some real simple shapes. The first shape we're going to look at is a simple plane. So when we say simple planes, we're just looking at vertical and horizontal planes because their equations are very simple. So if we look at this first diagram, you see we have the equation x is equal to 0. So that means that y and z can be anything as long as x is equal to 0. Now if this was two-dimensional space, x is equal to 0 would be a vertical line, but it's three-dimensional space, so it's a vertical plane. Notice that this plane is going to cross over the z-axis, and it's also going to cross over the y-axis. So because z and y can be anything, and this plane crosses over the z and crosses over the y-axis, we actually call this the y-z plane. And points in this plane will take the form of, remember the x is always 0, so y and z can be anything. I'll just throw in variable b, c. Any plane parallel to the yz plane will also be equation with just x, because the x value is fixed. The y and the z can vary. So in this second example, we have x is equal to 2. This plane is parallel to the yz plane, x equal to 0. And then points on this plane will always have the form 2, BC. So again, the y and the z can be any real number. Well, we'll look at another vertical plane, and that would be in the middle diagram, y is equal to 0. So this particular plane will cross over the z, and it'll also cross over the x. So this is our xz plane. And then points on the xz plane. The y is always 0, but the x and z can be anything. So these points take the form of some a value, comma 0, comma some c value. And then if I look at any plane parallel to the xz plane, say this next one where y is equal to 4, points on this plane will always take the form of A, comma, 4, comma, C. And then our last plane that we're going to look at, our last simple plane, would be z equal to 0. So it crosses over the x, or crosses through the x and the y axes. So this would be the xy plane. And then the plane z is equal to 0 has points of the form a, comma, b, comma, 0. And any plane parallel, say z equal to 3, will have points of the form a, comma, b, comma, 3. Example 3 asks us to find the equation of the plane parallel to the xz plane and passing through the given point. So if we look at A, we can see that the y value here is 2. Remember, this is parallel to the xz plane. So if we go back to our diagram and we look at the xz plane, which would be this middle diagram, we can see that any plane parallel to the xz plane is just the equation y equal to some number. So all I have to do for this first point is look at this y value of 2, and that's the equation of the plane. And that would be true for part B and part C as well. All of these planes are parallel to the xz plane. So to write the equation, all I have to do is simply look at the y value. So y equal to 7, and then y equal to 3, which is why we call them simple planes, because they're very easy to define. Something else that comes up when we're talking about points in our coordinate system is the idea of distance. Similar to the distance formula in two-dimensional space, when we talk about 2 points in three-dimensional space, it's still the square root of, subtract the x's and square them, plus subtract the y's and square them, plus subtract the z's and square them. So exactly the same. If I was going to find the distance between the points -1, 2, 3 and -5, 7, 5, all I have to do is subtract the x's, and it really doesn't matter the order because we're squaring. So I could do -1 minus a -5 or plus 5 squared plus 2 minus 7 squared plus 3 minus 5 squared, and then take the square root of all of that, which would be equal to the square root of 16 plus 25 plus 4, or the square root of 45. So something to remember is that we can simplify this because it's 9 times 5 and 9 is a perfect square, which would give me 3 square root of 5. So don't forget your algebra, even though we're already in Calc 3. Something else we can talk about with points is we can talk about the midpoint between points. So when we talk about the midpoint, it's going to be a point. So the formula is add the x's, divide by 2. That will give you the first coordinate. Add the y's, divide by 2. That will be the second coordinate. Add the z's, divide by 2. That will give you your third coordinate. Now remember, this is a point. So if we're going to find the midpoint between -1, 2, 3 and -5, 7, 5, we simply add the x's, so -1 plus a -5, or -5, and divide by 2. So remember, this is a point. So we write it as an ordered triplet. So this would be 2 plus 7 over 2 and 3 plus 5 over 2. So simplified, I should have a negative 3, 9 halves, and 4. Okay, moving on to another shape that we see quite often in three-dimensional space. We're going to talk about spheres and then a ball. So the sphere is hollow, a ball is solid. When we look at the equation of a sphere, it's similar to the equation of a circle, but since it's in three-dimensional space, it's going to have a z value as well. So it's going to have a center, some center ABC, and the equation is x minus a squared plus y minus b squared plus z minus c squared. That's going to be equal to r squared. So the difference between a sphere and a ball is, since the ball is solid, the equation is going to be the same on the left-hand side, x minus a squared, y minus b squared, z minus c squared, but instead we have a less than or equal to r squared. So that gives us the solid piece. Everything inside the sphere is included. Let's do some examples. Example 5, we're supposed to find an equation of a sphere. We have the center, and we know that it's passing through the point negative 3, 4, comma 5. And then we're also asked to find the equation of a ball, same center, passing through the same point. And it says on its boundary. So the boundary means the sphere itself, not the inside portion. So since our sphere has a center negative 1, 2, 0, that would be in the equation, my A, 2 is B, C is 0. So the equation is simply x minus a negative 1, or x plus 1 squared, plus y minus 2 squared, plus z minus 0 squared, so just z squared. And that's equal to r squared. So that's my equation. The problem is I need to figure out what r squared is. So I know that this is going to be passing through the point negative 3, 4, and 5. So all I have to do is simply put in negative 3 for x, 4 for y, and 5 for z, and I can find my r squared. So this is going to be 4 plus 4 plus 25. It turns out to be 33, I believe. Notice that I really don't need to find out what r is. All I had to do was write the equation of this sphere. So I just needed the r squared. So when I look at the sphere, the equation is going to be x plus 1 squared plus y minus 2 squared plus z squared equal to 33. So to write the equation of the ball, I simply have to replace the equal sign with the inequality. So that would be x plus 1 squared plus y minus 2 squared plus z squared less than or equal to 33. Let's do some more examples. Example 6 asks us to describe the set of points that satisfy the given equation. Oops, actually this should not say equation, it should say inequality. So I see that there's a less than or equal to. So I'm thinking that it's probably going to be a ball. So if it is a ball, I'm going to need the center and I'm going to need the radius. for me to write the equation. So going back to your algebra, to get the center, we have to complete the square on the x, the y, and the z. So my first step is to rearrange this so that the x's are together. So I'm going to write x squared plus 2x. The y's are together, so plus y squared, and there's no other y. And the z's together would give me a z squared minus 4z. And that would be less than or equal to -1. So all the constant numbers are going to be on the right-hand side. Everything with a variable is going to be on the left-hand side. And now I need to complete the square. So if we look at x squared plus 2x, that's not a perfect square. That's not something squared. However, if I add 1, then I'll get x plus 1 quantity squared. So remember, the process of completing the square is to take the linear term, or coefficient, in this case it's 2, take half of that and square it. So this would be x squared plus 2x, and I'm going to add 1. Again, the reason why I'm adding 1, which is half of 2 squared, is so that this turns into x plus 1 squared. The y squared is already something squared. Notice that I don't have a linear y term, I just have y squared. But the z's need to be a perfect square as well. So if I take half of -4, which would give me -2, and I square it, I get a positive 4. So this would be z squared minus 4z plus 4. And once I add 4, this becomes z minus 2 squared. But I have this y squared, and this is less than or equal to, I have to remember, if I add 1 and I add 4 to the left-hand side, I also have to add 1 and 4 to the right-hand side, so the inequality is unchanged. And now I'm done. This is x plus 1 squared plus y squared plus z minus 2 squared less than or equal to 4. So if I were to describe this, it's a ball with a center of -1, 0, 2, and radius of 2. And let's do one last example with our spheres and the balls. But this time what we're going to do instead is look at the intersection of a sphere and a plane. So think about a sphere and a plane. If I intersect them, it's possible that they will intersect and form a circle. However, the plane can just touch the sphere. In that case, maybe it'll intersect in a point. If the plane is slanted, it would intersect the sphere at maybe an ellipse. Okay? But we're just looking at a y equal to -2. That would be a vertical plane. So before I do the algebra, what I'd like to do is just do a quick sketch. And I don't want it to be that fat one, sorry. So this sphere here is a sphere with the center 0, 0. And it has a radius of 4. So this sphere kind of looks like this. I'm not very good at drawing in 3-dimensional. So that would pass through 2, 2, and 2 on the x, y, z. Now this plane is y equal to -2. So if I kind of look at the y as coming back here, that would be its negative side. Oh, I'm such a terrible artist. At -2, I could draw my plane. So it looks like it may intersect in one point, and sorry about my drawing, it's pretty bad. So what we're going to do is we're going to figure out algebraically where these guys intersect. So I know that y is equal to -2. So all I really have to do is substitute -2 in for y in the equation of a sphere. Now, algebraically, the way you find intersection is you usually just set things equal to each other and solve. But if I set these two equal to each other, I've got 3 variables. If I let y equal to -2, then I've got two variables in one equation, so I can't solve it. But what I'm going to do is I'm just going to replace y with -2 to get the equation x squared plus, if y is -2, this is 4, plus, z squared is equal to 4. So subtracting 4 from both sides, I get x squared plus z squared is equal to 0. And now I have to solve that equation. Okay? So I got one equation but two variables. So normally this would be pretty hard to solve. But I can see that the only solution here would be when x is 0 and z is 0. Notice there's no other x value or z value besides 0 and 0 that would work here. Because any other quantity, I'm going to square it. It won't be 0. And I'm going to add it to something else. So the only way to get 0 is if they're both 0. And I already know that y is equal to -2. So that tells me that 0, -2, 0, this point is the intersection of this sphere and this plane. And from my sad diagram, it looks like it's just one point. So let's go ahead and move on from points and planes and spheres, and we'll start talking about vectors. Now, vectors in R3, so remember that notation is just 3-dimensional space. The R just means real numbers. Okay, so in this diagram we have some vectors. We have our position vector, so that would be with tail at the origin. And we have some other vectors in here, such as PQ and RS. Those would be vectors that are equal to our vector PQ because they have the same magnitude or length and they're going in the same direction. But we can also talk about parallel vectors. So if and now let's look at the vector PQ. Let's say I have some point here, and I'll just call this W. And I have a vector that goes from W to P. Well, the vector WP is going to be parallel to the vector PQ. Notice that they're not going in the same direction, and they don't even have the same magnitude. But I can put them into the same line. So WP is parallel to PQ. So we use those slashed lines to indicate parallel. So parallel vectors are vectors that are scalar multiples of one another. In example 8, we want to check to see if these two vectors are parallel. So, are they multiples of one another? Well, the easiest way to do this is just to look at the first two components of the vector. So I have a -2 and I have a +1. Well, I notice if I take 1 and I multiply it by -2, then I get the first component of my first vector. So if I take -2 and I multiply it by 1, -2, 7/2, do I get the other vector? Well, this would give me -2, +4, -7. So yes, these are parallel. They're parallel because they are multiples of each other. And it doesn't matter which one is a multiple of the other, because I could have easily taken -1/2 and multiplied it by the first vector, -2, 4, -7, and that would give me a +1, a -2, and a +7/2. Okay, so now we're going to move on and we're going to look at operations of vectors in three-dimensional space. So it's similar to what we had in two-dimensional space. If we have two vectors u and v, then when we add them, we're just going to add them component-wise. So u⁻1 plus v⁻1, u⁻2 plus v⁻2, u⁻3 plus v⁻3. And it would be the same for subtraction. You have to do it by components. You just have to watch the order. If it's u minus v, it's u⁻1 minus v⁻1, and so on. And then if you're going to multiply a scalar or a real number by your vector, you have to distribute it to every component in the vector. So magnitude is length. So if you have a vector with tail at P, head at Q, and we write it as P to Q, then the components would be subtract the x's, subtract the y's, subtract the z's in the order of head minus tail. And the magnitude is still going to be the same notation that we have in two-dimensional space, and in fact it's the same distance formula. We just have a z component. So in two-dimensional space, we talked about our unit vectors. I was 1, 0 and j was 0, 1, but now we have a z component. So I is still going to be the unit vector on the x-axis, so that would be 1, 0, 0. J is going to be a unit vector along the y, which would be 0, 1, 0, but now we have the unit vector on the z-axis, which would be 0, 0, 1. And then we have any vector can be written in terms of the unit vectors I, j, and k. In example 9, we're going to compute the magnitude of vector u plus 3 times vector v. So that's going to be exactly the same as what we did in two-dimensional space. The first thing I want to do is write down what u is. And it helps if I actually tell you what u is. So -340, that's going to be my u. And 311, that's going to be my v. Oh, it's terrible. So u is going to be -340 plus 3 times v is going to be 311. which is going to give me the vector -3, 4, 0, plus 9, 3, 3, and then adding these two vectors together, I'm going to get 6, 7, 3. So the magnitude is just our distance formula. We're going to have 36 plus 49 plus 9, and then we're going to take the square root, which is going to give me the square root of 94. And I don't think this can be reduced. So let's try another example. If you recall from two-dimensional space, if I had to find vectors that are parallel to another vector given a certain length, the first thing I want to do is take my vector and write it as a unit vector. And once I write it as a unit vector, then I can multiply it by whatever length I need. So if I had to find two vectors, they have a length of 20, and they're parallel to the vector -3, 0, 4, then the first step would be to write the vector -3, 0, 4 as a unit vector. So I'm going to take this vector and I'm going to divide it by its magnitude, which is the square root of 9 plus 16. And that will give me a unit vector. So I want two vectors that are parallel to this vector, -3, 0, 4, but of length 20. So if this is a unit vector, all I have to do is multiply it by 20 to get a vector of length 20. But if I take the positive and the negative, then I have two vectors of length 20 that's parallel to the vector -3, 0, 4. So the key is to take your vector and write it as a unit vector. So this is going to be plus minus 20. The vector is -3, 0, 4. And we're going to divide it by the square root of 25, which is 5. So I can write this as plus or minus 4 times my vector. And we could leave it like that, or I could distribute the 4. I'm just going to leave the plus minus on the outside to get -12, 0, 16. So these are two vectors parallel to the given vector with a length of 20. However, there was more to this problem. It says write in terms of the unit vectors. So the unit vectors are going to be the I, j, and k. Now I don't want to keep a plus minus on there when I do the I, j, k because it's going to be a string. So I'm going to do the positive, which is the -12i. Notice the j has a 0 coefficient, so I'm not even going to write it. I'm going to do a plus 16k. So that would be one of the vectors. And the other vector would be the negative, so that would be a positive 12i minus 16k. All right, so these are my two vectors that are parallel to my original vector with a length of 20. So let's look at another definition. In example 11, we're told that points are collinear if they lie on the same line. And then we're going to determine whether the points that were given, P, Q, and R, are collinear. And the way that we're going to do that is by comparing these two vectors. So with these two vectors, I'm going to just pick one of the points, and here in the directions we chose P to be the tail in both vectors. So PQ, PR both have tail of P. And it didn't really matter if I did PQ, PR. I just have to take one of these 3 points and choose one to be my tail, and then define the two vectors with different heads. Okay, so let's think about this. Collinear means it's going to lie on the same line. So let's just say that I have this vector P, Q, and it looks something like this. Well, the other vector PR, maybe it's longer. Or it could be shorter. The thing is that these vectors are going to be parallel. It's also possible that you could have PQ and maybe the other vector PR goes in the opposite direction. But notice even if it does go in the opposite direction, the two vectors are still parallel. Okay. So comparing the two vectors PQ and PR tells me if they're parallel, then PQ and R, those points, are going to be collinear. They're going to lie on the same line. So the first thing I want to do is look at these two vectors and first compute them. The vector PQ is going to be equal to Q minus P. So Q minus P is going to give me 3, negative 2, negative 1. And then when I look at PR and do R minus P, I get negative 12, 8, and 4. Okay, so are these parallel? Well, if I take negative 4 and I multiply it by PQ, which is 3, negative 2, negative 1, then that's going to be equal to negative 12, positive 8, positive 4. So these guys are parallel. And since they're parallel, it must mean that they're collinear, because not only are they parallel, but they have the same tail P. All right, so I know they're collinear. The question is here. Which point lies between the other two? Okay, well, P is the tail. Okay? So either you start at P and you go a direction QR in the same direction, or you start at P and you go in opposite directions. To go in opposite directions, one has to be a negative multiple of the other, because a negative means opposite. So since I'm taking negative 4 times one vector, I'm changing the direction of one vector to go into the direction of the other. So it must be the case that P is between the two. So I didn't even have to graph these. Okay? I could see that it's collinear where P is between Q and R. So a lot of theory there. Not a whole lot of math or computation. Okay? And again, the key was that they're parallel, but one is a negative multiple of the other, so it's going in a different direction. And they share the same tail. So same tail going in opposite directions, the tail must be the point between. Let's look at our last example, and this is similar to the example that we saw in the previous section. We're going to be looking at a plane flying horizontally. It's going due east in calm air. It's traveling at 250 miles per hour. It encounters a horizontal crosswind blowing northwest at 50 miles per hour, and then an updraft of 30 miles per hour. So we want to find the resulting speed of the plane and describe its direction. So the first thing I'm going to do is I'm going to draw a diagram to model the problem. And since this is giving directions like north, west, and east, I want to label my axes with the direction. Sometimes it's a little hard to see when you're in three-dimensional space with an X, a Y, and a Z. So if I were to just look at the two-dimensional space, that might be easier to see. So remember north, south, east, and west. So we know that our plane is flying due east. So on that two-dimensional space, I'm going to draw my plane flying due east. So notice that this plane is going on the x-axis in the positive direction. So I'm going to go back to my three-dimensional graph and draw my vector that represents the plane. I'm going to label it, and I think I'm just going to use P. So P is going to be the plane, and now remember this plane encounters some wind. So before the plane encounters the wind, then it's going to be relative to the wind that it encounters. I'm just going to say to the air. So remember, when we say relative to the air, it means the plane without the air affecting it. And here when I talk about air, I'm talking about the crosswind and the updraft, both of those. So the speed was 250 miles per hour, so that would be its magnitude. And since it's just going in the direction east, again, it might be easier to see in the two-dimensional diagram. Then I write the vector only in terms of I. So it's going to be 250I. Oops, if I could draw 250. And then remember that you can always write the vector in vector notation with the vector brackets, which would be 250, comma 0, comma 0. And it doesn't matter to me which notation you use. So this plane is going to encounter a horizontal crosswind blowing northwest. Okay, so I'm going to go back to my two-dimensional diagram, and I'm going to draw northwest. So remember, northwest is halfway between north and west. So that would be the positive y-axis, but the negative x. So I would have some vector on the three-dimensional space that looks like this. That would be northwest. So what am I going to call this vector? I think since it's called a crosswind, I'll use C for crosswind. And I'm going to write the vector representation of my crosswind, but I need to figure out, I'm going to use angles, okay? I know the magnitude is 50. So if I were to look at the angle, it should be 135. And here we're in degrees, which means my vector for the crosswind is going to be magnitude cosine 135 I. So the magnitude is 50 times cosine of 135 degrees I plus 50 sine of 135 degrees J. And notice there's no K component because it's a horizontal wind. If you would like to write that using our vector brackets, make sure that you remember all your trig values. Typically, we don't use a calculator until the very end to make sure that we're rounding accurately. So cosine of 135, that second quadrant, is going to be negative square root 2 over 2. And thinking, should I just simplify it now? I think I'm going to simplify it now. So if cosine of 135 degrees is negative square root 2 over 2, this becomes a negative 25 square root of 2i. And then it's going to be a plus, sine of 135 is positive square root 2 over 2, so plus 25 square root of 2j. Or using vector brackets, it's going to be negative 25 square root of 2, comma, positive 25 square root of 2, comma, 0, because we're in three-dimensional space. Okay, so going back to our problem, it encountered a horizontal crosswind blowing at 50 miles per hour, so we have that. And now we have an updraft of 30 miles per hour. I'm going to use U for updraft. So when we say updraft, this is a vertical wind blowing straight up. Okay? So I can't show that on my two-dimensional space, but I can show this in my three-dimensional coordinate system. So here we have our crosswind, and now I have an updraft. Our updraft has a magnitude of 30, and notice that it's on the z-axis. So x and y are 0, and my updraft is simply 30k, or 0, 0, 30. All right, so I got all this down. Now the question is to find the resulting speed of the plane and then describe its direction. So the resulting speed, when I say resulting, it means the plane, the speed of the plane with the crosswind and the updraft affecting it. So in other words, it's going to be the plane relative to the ground. So when we talk about relative to the ground, it means if you're on the ground looking at the plane, you are observing its speed with the crosswind and the updraft affecting it. Okay, so this would be the resulting plane. Or relative to the ground. And since we're looking at the plane with all these currents affecting it, it's going to be the plane without the wind plus the crosswind plus the updraft. So I'm not going to do ijk. I'm just going to add the 3 component y's going back to these 3 vectors in vector notation. If you add 250 plus 0 plus the negative 25 square root of 2, then we get the vector 250 minus 25 square root of 2. That would be the first component, our x value. The next one would be the 25 square root of 2, and then the last would be 30. So this is the vector that represents the plane with the crosswind and the updraft affecting it. So I need to find the speed. Well, the first thing I'm going to do is I'm going to go ahead and look at this 2-dimensional diagram. Now, if I was looking at how the crosswind affects my plane, so this blue vector is my plane, the crosswind is blowing my plane, so it's going a little bit to the north. But notice that the direction of this crosswind is also slowing my plane down. Okay? It's going kind of against the plane, so it's going to slow it down. And then when you think about an updraft, this plane is going to be pushed towards the north, and then the updraft is going to start pushing it up. Okay? So going up to the 3-dimensional, if we look at the updraft, that's kind of slowing it down as well. So before I even compute my speed, I'm thinking it's going to be less than the original 250 miles per hour. So if we were to compute the speed, remember that's going to be equal to the magnitude of this plane, which would be 250 minus 25 square root of 2 squared plus 25 square root of 2 squared plus 30 squared. And I'm going to take the square root of all of that. So double check me on this. I'm just going to plug this into a calculator. And now I think I'm just going to round it to the nearest whole number and write, I think I have 220 miles per hour. That seems reasonable because before the crosswind and the updraft affected the plane, it was at 250 miles per hour, and I knew that both of those would be slowing down the plane. So this seems like a reasonable answer. Let me know if I messed up putting this in my calculator. So in the question, it just says to describe its direction. It doesn't say to give a heading or anything like that. So all I have to do is just simply describe the direction. So when we talk about the direction, and it would be when I talked about the diagrams, notice that the plane is going upward and a little bit north. So it started out at east. So when I describe it, I'm going to say the direction is north of east. So it started out east and now it's going a little north and upwards. At this time, I'm not going to talk about headings and figure out a theta value. I'm just talking about the general direction that the plane is now going in. Okay, so that's it for 13.2.